Okay, I guess we better start. Well done to those of you who made it at 9 a.m. For optics, gosh. Okay, so we're going to start today on a new topic, or more accurately, an extension of what we've been talking about. So we've been talking quite a lot about the two-slit experiment and trying to figure out how that works, how we find out the interesting features of maximum, minimum intensity. We also yesterday derived the full intensity distribution. And now we're going to go on to the diffraction grating. So this is essentially an extension of the double slit experiment, and you treat it in very much the same way. It's got more slits, right? So if you were to want to figure out the full intensity distribution of this, you could still represent your waves with by complex amplitudes and add them all up. It's just that you would have n of them, where n is your number of slits, rather than just 2. So diffraction gratings can work broadly in 2 ways. There's transmission or reflection grating. So a transmission grating really is, essentially what we've been talking about before with 2 slits, except there's more slits. So it's just like a plate with sort of finely ruled sort of holes or slits. Whereas a reflection grating is, it works in the same way really, but it's just like a mirror, and if you kind of imagine sort of painting, black lines on it or something, so that only some part of it was reflective, then that would work as a reflection grating. So the maths of both of these things is exactly the same. Actually, in practice, mostly it is reflection gratings that are used these days. But we're going to, just because it's easier to draw actually, we're going to look at a transmission grating specifically, but the maths is absolutely identical. Now, it's actually not on syllabus this year to do the full intensity derivation. It is next year. However, it's not very difficult, so I'm not going to do it because it's not on syllabus, so we don't have time to do it. But if you want to go away and actually, derive yourself for your own edification, the full intensity distribution, it's really not difficult. It's just rather than summing up 2 complex exponentials, you sum up n of them. You have to sort of pull a few tricks to get the sum into a nice form so that it becomes like a series. But anyway, it's not actually too difficult. So you'll be able to find it in books like Hecht. We are just going to talk about the basic properties of diffraction grating. So, figuring out where the maxima are, why, essentially, we're going to discuss why the fringes that you'll see, or the peaks that you see, look the way that they do. So that's what we're going to do. What was I going to say? We're just going to use basic arguments to look at the basic properties. Oh yes, and specifically, we're going to essentially concentrate on the case where n is very large. So the number of slits is very large, essentially infinity. So we look in detail at the 2-slit case. That's what we've been doing so far. We look in detail, some detail, at the n equals infinity case, and we don't really concentrate at what's in between. But I may just touch upon it depending on how time goes, how things would look for some sort of finite number, more than 2, less than infinity, just so that you have some idea of what's going on in the in that in-between region. Right. So yes, the basic property is easily understood from just some basic arguments, simple sketches. So that's what we're basically going to do. So here's our diffraction grating. Having said I'm going to concentrate on an infinite slit diffraction grating, I've now drawn a 7-slit. Because I have a finite size to my slide. So what's going on? The plane waves are coming up from below. Each of these slits is going to produce circular waves, or cylindrical waves, but circular in 2D, just as we had for the 2-slit. So there's the one coming from the middle slit there, from the 2 either side, from the 2 either side that, and the 2 either side that, right? So this is starting to look a little bit messy, and you might think, well, goodness, how on earth are we going to analyse that, especially if I had infinity of these things? But it turns out it's not actually too difficult. And the first thing to realise is that you have some sort of Huygens-style reinforcement of these waves, right? So we're going to have some sort of forward-going wave where these waves reinforce each other. These blue lines would just correspond to the sort of straight-through wave, so essentially the n equals 0, the central peak, if we were thinking about the 2-slit experiment, is the analogue of that. But we're also going to get reinforcement in some other directions, where the waves are again going to reinforce each other, And it might not be completely obvious what those particular envelopes are corresponding to, so I'll simplify the diagram a little bit. What I've basically drawn there is the tangent to, so the 0th wave coming from this slit, and then from the first slit I've let, you know, this wave sort of go one wavelength on, so it's another wave is sort of just about to appear here. From the next slit, sorry, it's the second one, third one, fourth one, fifth one. So I've basically just drawn the tangent to the waves for the situation that each successive slit is sort of one wavelength extra, if you see what I mean. Okay, so let's analyse this a little bit more. So now I've drawn on the rays instead. So these blue lines are the rays representing the direction of propagation of the light. So these are all perpendicular. So the green ones are the wave fronts. They represent where the waves are all in phase. That represents that. And then the blue are the rays, and they are perpendicular to the wave fronts. Okay, so the length of these lines from this situation, they're all going to be different by one lot of lambda, right? Because that's what we drew. If I flip back to the previous slide. They were all sort of one wavelength different in length, so I'm just labelling that on there. And so that leads us to the condition, essentially, that in order to get reinforcement, in order to get constructive interference, we need each of these optical path lengths to differ in length by some integer number of wavelengths, right? And then everything will add up, everything will all be nice, and we'll get bright peaks in our pattern. So let's do a little bit more of the very, very basic maths here. So I've just simplified the diagram. I've just chosen one of these lines because we don't need them all. So I'm defining theta to be my angle between the ray and the normal to the grating. That's what that dashed line is. Now, if that's theta, this is a right-angled triangle. Remember, that was the wavefront, that was the ray. So that's also theta. And then along the bottom here for this 7-slit grating, it turns out I've drawn, is that's 6D. Right, so what I want you to put in the box is just a very simple, just couple of line thing. So we're just doing simple geometry now. So you can see that sine theta, equals 6 lambda over 6D, which equals lambda over D. Hope you all agree. All right. So that leads to a simple diffraction grating equation that, if that's true, then we get constructive interference. But that's not the whole picture. This is not the most general equation, because what if, for example, I replace my light with light that was actually half the wavelength of what I had before, right? So this is the same diagram in terms of the length of the lines, but now that, you know, this one's 2 lambda, this one's 4 lambda, this one's 6 lambda, and so on, because my wavelength is half what it was before. But clearly I'm still going to get constructive interference in that case. Everything is still different by some integer number of wavelengths, so this is fine. This, you know, as long as that's true, I will get constructive interference. So the more general diffraction grating equation is this one, that d sine theta must be some integer number of wavelengths. Okay? So that's basically just saying that the optical path difference between any two adjacent slits, right, so that length there that I'm trying to point to is d sine theta. As long as that length is any integer number of wavelengths, we get bright peaks, we get constructive interference. This is the grating equation that you must remember for diffraction grating. If you just remember that, you'll be doing all right. Okay, so let me in fact just do a bit of an illustration of what the peaks are going to look like. So turn the lights down again, and what the peaks do look like. So this is a diffraction grating here. Right, so can you see those spots on the ceiling? Oh, right. So they're very small compared to, so each spot is very small compared to the 2-slit that we saw, and they're very, very, more noticeably, they're very, very widely separated. Right, if you remember the 2-slit, we saw the fringes, we now know that they're this sort of cos squared type modulation of the intensity because we derived that. They were quite close together, not very well separated in comparison to that. So we're going to spend some time in this lecture basically talking about not only the peaks that you saw, but why there's essentially nothing in between, right? The other thing to notice is that they were quite widely separated compared to the two-slit case. So you'll notice when I'm talking about diffraction gratings, I am not going to be using the small angle approximation. I'm going to keep this in its full trigonometric form because actually you can get quite large angle peaks. Okay, so before we sort of concentrate on why exactly you saw what you saw, and by that I mean, okay, we found out the position of the peaks, but why do we see essentially nothing in between? Before we talk about that, let's just talk about the application of a diffraction grating, and we're going to talk about its use for dispersing light. So, and what it actually does. So, let's just consider some white light. So I'm just going to take it to be composed of red, green and blue, make my life simple. And take my value of D, the spacing between the slits on my diffraction grating, to be 1.5 micrometers. This is just a typical value. It does tend to be much smaller than a typical value for a two-slit experiment, for example. And the diagram that is about to come up on the slide is drawn pretty accurately, or, roughly accurately for these numbers that I've just chosen, right? So that's why I've put the numbers there, because what you're about to see is kind of realistic for that. So herein comes my red light. I mean, imagine I'm shining white light, but I'm just going to decompose the colours to show you what happens to each of them. So here's my red. There's some central peak, which corresponds to n equals 0, because if you have n equals 0, you have theta equals 0, so that just goes straight through. Then I'm going to have some wider angle peaks. They're my n equals 1, my first order peaks, and then I can have n equals 2 as well, and that is the n equals 2 turns out to be the maximum order, given that I need to constrain sine theta to be between 0 and 1, so theta between 0 and 90 degrees. Okay, so here's my green coming in. Obviously I'm going to get the n equals 0 peak straightforward there as well. This is going to be dispersed a little bit less because green has a smaller wavelength, right? So according to that, won't scatter to quite as big theta. Then I've got my n equals 2 again, and you can see that the difference, the sort of angular distance between the two wavelengths becomes larger at larger orders. Okay, blue, very much the same thing. Here we have the n equals 1, the n equals 2, and actually there's a third solution between a theta of, between 0 and 90 for blue with these numbers that I've chosen as well. So we get actually a third order peak if we were to solve this equation as well. Okay, so what you'd see if this really was white light, you'd see this sort of bright white central peak. You'd then see a group of coloured dispersion here, another group of coloured dispersion, and some blue edges. Right, that's what you would see. And this is what diffraction gratings are used for, right? You're used for sort of trying to analyse the different wavelengths in a particular light source. So you want to split out the spectra and be able to sort of identify the different wavelengths. Okay, so in order to sort of understand that a bit more, we need to work out something called the angular dispersion. So that is simply, I'm using another big D here, right? Obviously this is a completely different big D to the distance big D that we've been using. So I'm just, so sorry about that, there's a lot of D's in this course. I'm just going to call it that, not even bother to give it a particular name. This is the thing that we want to work out. Yeah, probably this is what you want to put in the box. Okay, and the point is, let's say I have two wavelengths quite close together. I've got lambda and lambda plus a little bit more, right? Or a little bit less. Lambda plus delta lambda. And what I want to know is that for such a separation delta lambda in wavelength, what does that translate to in terms of a difference in angle that I'm actually going to see, right? So this is my relationship that I will need to use for that. Right? So I need to know this sort of, this term here in order to translate a difference in wavelength into a difference in theta that I will actually see. And of course in practice what you're doing is doing things the other way around. You would measure a difference in delta theta, you would use this relationship to figure out therefore what difference in wavelength you've actually got in your source. Okay, so let's figure out d theta by d lambda, this angular dispersion. So we're going to start from our grating equation. Now I could, if I wanted to, just rearrange this to get theta in terms of lambda and actually do the differentiation. And some of you will know the derivative of sine to the inverse sine, but I'm not going to bother to do that. I'm going to do implicit differentiation instead, because it's usually easier. So d cos theta d theta. All right, so I've got d theta by d lambda equals n over d cos theta. And I'm just going to put that also into a different form. 1 minus sine squared theta to the half. And because my sine theta is n lambda over d from my grating equation, let's just do it a bit more. So d into 1 minus n lambda over d squared, all to the half. Let's just get it into its simplest form. So n over d squared minus n squared lambda squared to the half. Right, so that's my angular dispersion. So this is the relationship that I would need to use if I wanted to convert a small difference in wavelength into a small difference in theta, or of course vice versa. Right. So what you can see from this then is that you would expect, as you go to higher orders, because of this sort of proportionality to n up the top, you would expect as you go to higher orders that the dispersion increases, right? And that is what we're seeing. We're seeing this separation between the blue, green, red here getting larger for n equals 2 than it was for n equals 1. And that increase in dispersion is not actually linear because of this denominator going on here, right? So in order to get the maximum dispersion, and that's a good thing, right? If you can separate these things at wider angle, you can therefore identify smaller wavelengths, right? And you can go down to smaller, closer wavelengths, which is a good thing. So to get the best dispersion, you want something like, or you want to choose d of order n lambda. Something like that to give you very large dispersion. Now you might think that what you want to do is go up to the highest order possible. Clearly we can see n equals 2 has a wider separation here than n equals 1. But actually the problem is in practice you start to get what we call overlapping orders. So the fact that you've got this n equals 3 blue order coming in, it starts to overlap with the others and you don't quite know where you are essentially, which order are you seeing. So actually mostly in practice you work at n equals 1, where you tend not to have the complication yet from overlapping orders, but you choose. So work at n equals 1, usually in practice, and choose something like d around lambda. That's what people tend to do. So you choose a particular diffraction grating that's suitable for the wavelength roughly of the light that you're analysing. Okay. So what does a simple grating spectrometer actually look like in practice? This is quite a simple version. I mean, real versions these days would tend to be more complex, but sometimes in the exam, you're asked to draw a practical setup for a grating spectrometer. This is the thing you want to reproduce if you are asked to do such a thing. So let's talk about what's going on briefly. So here's your light source that you want to analyse. The wavelengths from it that you want to analyse. I'm putting it first through a small slit. What the purpose of that small slit is to try and produce a point-like coherent source. Right? Remember the importance of coherence in order to get your interference pattern. If you've got an extended source, as I said, you might have, you've got electron transitions coming from different parts of the source. They have no reason to be coherent, this constant phase relationship. They have no reason to be coherent with each other. So you want to put it through a small slit first to make it a point-like source, which is what you want. Okay, then I'm putting a lens here so that I can convert this, this light that's diverging from this point-like slit here. I can convert it into the parallel rays, so these are the plane waves that I want. This is my diffraction grating. It's diffracted through the light's diffracted through some angle theta. I'm going to then use another lens rather than observe at very large distances. Let's just use another lens to focus onto a screen or onto a detector, a piece of photographic film, or what have you. So this is the basic setup that you want to use. And then what you would do in practice, you're trying to measure the intensity of the light as a function of theta so that you can figure out what the wavelengths are. In practice, it's more usual actually to measure 2 theta. So you look at, maybe the n equals 1 peak, and then also the n equals -1, and measure the difference between that. You don't then have to know sort of where is my 0 point exactly. That's usually a more accurate thing to do. Okay, real design's more complex, as I've said. In an exam, reproduce that with some description of what these components are doing for you. Also a problem sheet question, I think. Okay, why use gratings? Why use a grating rather than a prism to disperse light? So we saw in the first part of the course in geometric optics, we looked at prisms and dispersion from that. Gratings do have many advantages. The dispersion can be very easily calculated from simple principles, and essentially the only thing you need to know about your grating is the slit separation D, which you know because either you made it or your trusty manufacturer told you what it is. You can adjust the amount of dispersion. That's a good thing by just using a grating with a different D. You could look at higher orders, although there is this, which is why I've put that, but there is some complication from overlapping orders there. But anyway, you've got control with your choice of this little d, the slit separation. Another big advantage is that for gratings you don't need transparent material. With the prism, of course, you're shining a light through it. You need that the light needs to go through it to actually disperse. Fine for visible light, not always easy for other wavelengths where glass is not necessarily transparent. So you don't need that with gratings. They do have a few disadvantages, gratings. One of the main one is that the intensity of the light is shared between different orders. You've got some going into your central peak, your n equals 0, some into n equals 1, n equals 2, and so on. So you're kind of spreading out the light. So if intensity is an issue for you, that could be something to worry about. In practice, so note this is a sort of brownie colour, which means you should have heard the phrase, but it's not strictly on syllabus. That issue can be improved by using a technique called blazing the grating. Essentially, you do it again in the second year briefly. Look it up in a book, but essentially you sort of make your grating a bit of a dog tooth shape rather than flat. You can choose the angle of this dog tooth, particularly to basically direct most of the light into a particular order that you're interested in. It's quite an interesting technique, but not on syllabus for you here. Just look it up in a book if you are interested. Okay, natural diffraction gratings. Just a bit of a, light relief, this slide, and sit back. One of the... there's a few in nature, actually. One of the really lovely ones is this butterfly, which you probably, you may well have seen in natural history museums or on, programs, natural history programs or something. So this butterfly is just so blue, the blue morpho, almost too blue to be true. But actually, it's got no blue pigment at all. It's actually brown in terms of its pigment. How it looks like that is that its wings are scales, and they're sort of designed in so as to be a diffraction grating, essentially, which directs all the blue light to your eyes. So that's why they look like that. Opals, semi-precious stone, they've got an internal structure which also acts as a diffraction grating, and just a normal CD as well. Those grooves, very fine grooves, act as a diffraction grating. So if you've got a CD, and you can, obviously these these colours are already the effect of it being a diffraction grating, but if you were to shine a laser on it, you would see these diffraction peaks. Not quite as sharp as this actual diffraction grating, but it works nicely. Okay, so I'm going to take a bit of a pause just in case there's questions, but what we're going to do now is move on to looking at the region between the peaks. So just while I gather myself. Any questions, or are you okay? Take a sip of coffee. Right. Okay. So let me show you again the pattern, just to remind ourselves once again. So, okay. So here we are. There's the diffraction pattern on the ceiling. You see these very widely spaced bright peaks. Actually, we are seeing something a little bit in between. It's very, very faint. So I will try it, and the reason we're seeing something in between, actually, can you see that there is a faint red line? Can you see that? The reason we're seeing that is because this is not an infinite slit diffraction grating. So I will try and talk about why exactly we see what we see. Now that line seems to have disappeared, but it was there. Okay. So the difference, as I've said, between the two slits is that these are very widely separated, very tight peaks, and then essentially no intensity in between. So we're going to talk about why that is the case. Why do we see what we see? So I showed a diagram a bit like this a few slides ago when we were discussing the directions of the peaks, but the lengths of these lines in that case all differed by some integer number of wavelengths. That was what gave us the constructive interference. Now you could imagine looking in some other direction instead, somewhere between the central peak and the n=1 peak. Look somewhere in between, in that sort of darker region we saw. Right? And at some point, you can understand certainly easily why right in the middle is going to be dark, because that corresponds to this diagram, right? So at some angle, I'm going to come across a point where the length of these lines are all different by half a wavelength, right? Rather than a whole wavelength, they're different by half a wavelength. And so that is just like exactly the same as the region in between the two slit experiment. It's the point where all the phasors are half a wavelength difference, so equivalent to pi difference, so phi equals k delta, so that's 2 pi over lambda, that's lambda over 2, so they're all pi different, right? So that's representing it by phasors, so you can see that everything is just cancelling out, right? Now, as long as you've got, okay, this is just a 7-slit grating, so how many have I drawn there? Let's draw 7. 1, 2, 3, 4, 5. Right. 6, 7. With an odd number, if your number is small, I am going to have 1 left over, but we are talking about very large n, right? So even if I have 1 left over, it really doesn't matter if I'm talking about infinite number of slits, right? Everything's even. Okay, or very large number of slits. So essentially you can see why everything is going to cancel out in the region right in the centre, and we're going to get destructive interference there. But because I don't just have 2 slits, so that was the same as 2 slits, but I don't just have 2 slits, I've got lots of slits. So you can now imagine looking in other directions and also seeing cancellations, right? So here I'm looking at an angle where now the length of each of my paths is lambda by 3 more than the preceding one, right? So 3 of them together add up to 1 single wavelength. So I'm trying to draw the phasors here, so if my path difference is lambda by 3, then my phase difference k delta is 2 pi by 3, so 120 degrees, right? So each 3 of them are clearly going to form a closed loop, this equilateral triangle, right? So here's my phasor from the first, from the second, from the third, and so any group of 3 now are going to give me destructive interference. Groups of 2 won't, but groups of 3 will. And if I have many, many slits, then I'm going to have enough groups of 3 that everything's going to be black again, everything's going to be destructive. And I could go on and argue this more. I could have, look at another direction where my phase difference is, my path difference is lambda by 4, so my phase difference is pi by 2. Right, and any group of 4 now is going to form closed loops, right? So then if you've got an infinite number of slits, essentially you can imagine that in any direction I look at all, these phasors are all going to cancel out and I'm going to get destructive interference. Right? So that's why you only get peaks in that special direction where all the phasors are lining up nicely and you get constructive interference, and then in any other direction for an infinite slit grating, everything cancels out and you see nothing. Now, the fact that we were seeing something is because this wasn't an infinite slit, so they were, you weren't quite seeing complete cancellation. Okay, right. And the other thing about a real, diffraction grating that doesn't quite have infinite number of slits, but it's got many, is that there is going to be some width of the peaks. It's not, it's not going to be that your intensity distribution is like a load of delta functions, at d sine theta equals 0, lambda, 2 lambda, etc. It's not going to look like that. It's going to have some sort of narrow width, right? So we saw that there were spot sizes on the ceiling. So why is that? Well, that's because you don't have an infinite number, so you're going to have a situation, a sort of smallest angle, as it were, where you have complete cancellation. So that's what I'm trying to illustrate on this slide. If I go to some small angle, at some point, I've got a situation where it takes all of my n phasors all together to form a closed loop, right? So I need all of them, and so it's quite easy to find out what that position is. So what we need is, so I've got this closed polygon formed from all of my phasors, right, something like this, where the phase difference between each of these is k delta, and what I need, if I've got n slits, I need n lots of phi to equal 2 pi, right? I need all of them to form this closed polygon, and so my phase difference at the point when I first go to 0 in my intensity is 2 pi over n. Okay, or let's write that as a k d sine theta equals 2 pi over n, or d sine theta equals lambda over n. Right, so that is the position at which my intensity distribution first falls to 0. So let's just draw it again, because I'm going to need this in a minute as well for what I'm doing. So I've got some very narrow peak. The larger n you have, the smaller, I'll do it lambda over n, the smaller is this sort of angular width, right? Each of my peaks are separated, hang on, sorry, got to bring it down a bit, not tall enough, separated. There exists some integer number of lambda, and goes on 2 lambda, minus 2 lambda, etc., etc. And then the width of the peaks are at lambda by n, and if n is big enough, then essentially you see nothing in between, because you have some sort of destructive interference everywhere after this. Okay. Now, while I am, even though I said this was off syllabus, so we've concentrated on n is very large here, or we are concentrating on n is very large, I just said I'll touch upon, even though it's off syllabus, how this changes if you've got some sort of finite number n, so bigger than 2 but less than infinity. So I'm going to just briefly do that. There is no, predefined box for this, because it's, as I say, it's not on syllabus, but it might be useful. And anyway, you will do it next year. So let's just take one example. Let's say I have n equals 4. Okay, so I know, because it doesn't matter, the value of n doesn't matter for where my main peaks are going to be, right? They're always going to be at some integer number of wavelengths. But it's what's happening in between is the question. Right, so because I've now got n equals 4 and not n equals infinity, I'm not going to get cancellation everywhere in between. I will only get cancellation in certain directions when my 4 phasors can form closed loops, right? And there are 3 places at which that can happen. There's phi equals pi by 2, so I need just 4 of them to form closed loops. So there's phi equals pi by 2. There's the usual phi equals pi. And then there is phi equals 3 pi by 2. And those are the only places for n equals 4 that I can actually get zero intensity. Right? So I'm going to have, so lambda by 4, lambda by 2, 3 lambda by 4 are where my zeros are going to be. So I need to then join things up. Hang on. Wait a minute, that should be coming there. Right, something like that. Bit of a bad drawing. They should be equidistant, but anyway, there's minima. But anyway, so it's going to look something like that. And same this side. Right. Okay. So in general, it's true that for n slits, then I always have n minus 1 minima. This is always true. And sorry, it's getting a bit messy now with all my lines, but n minus 2 secondary maxima. I'm running out of space, sorry, secondary maxima. That's always true. And so then you can see that if you take n up to a very large number, then, I mean, given you're distributing the light as well between all these peaks, basically for n very, very large, you end up with something that looks like there's your main peak, and then you have a load of secondary maxima, but they're very small. Right, so that's what happens when you have n large but not infinity. And that's what we were seeing up on the ceiling, right? We saw this little bit of sort of band of light. Okay. Right, now we're going to use the ideas that we've just talked about. Specifically, we're going to look at this equation here to just sort of do a rough calculation of the size of one of these spots that we saw in the ceiling, the angular size. So it's in Brownie because it's it's something you should know about, but not strictly on syllabus. But we will see this calculation done again in a slightly more rigorous way later on. Well, next week it'll be now, I expect. But let's just see what's going on. So what I said was that my peaks first come to 0 at lambda by n, and I'm going to call this width. Sorry, can you see that? It's just the angular width, right, between the maximum and when I first go to 0. I'm going to call it delta theta. Right. So we know that d sine theta, let's just look at the central peak because it's the same for every peak. D sine theta equals lambda by n is the point at which I go to 0. So first 0 when that's true. So let's use the small angle approximation because these peaks are very small. I've called that width delta theta, and that equals lambda by n. And so delta theta equals lambda over nd, which is otherwise actually represented just as the width of the grating. Number of lines times distance between the lines. So here with my grating, you know, it's maybe 15 centimetres, 10, 15 centimetres. I've got, you know, visible light of a few hundred nanometres, so you can see why those peaks were very, very small. Okay, as I say, we'll come back to this and do this in a slightly more rigorous way a bit later. Okay, first of all, to get to those ways of calculating it, we need to talk about a better theory of diffraction. So far we've been just talking about two slits, we've generalized it to diffraction gratings. More generally, the more mathematical way of treating this is to think not of specific objects, not of a two-slit or a diffraction grating particularly, not from the start, but to think of some general aperture, some general object. Right, so I'm going to draw just a general aperture my light can pass through, right? So this is almost like a black box I'm drawing here, where I can replace what exactly this thing is with different things, right? It might be that I do have a two-slit in here, it might be, or I might have a diffraction grating in here, or I might have just a single open slit, as it looks like. Now, or I could do something even more complicated. I could put some sort of filter over this aperture so that it only lets a particular amount of amplitude through, not the whole thing, or that it even allows more amplitude through at the middle than it does at the edges, some sort of complicated thing. And we sort of want a general way to be able to treat some general aperture. So what we can do, and what we should do in general, is actually treat every point in here. There's supposed to be an infinite number of dots that I'm drawing here, but clearly I can't do that. Right, so we treat every point in this aperture as an infinitesimal source of light in its own right. Right, and we define its complex amplitude. So to give you an example, if what this aperture was the simple two slits. Oh, sorry, there's a slit. Right. What I would have is that my complex amplitude is 0, 0, 0, 0, 0, 0, all the way from here to here, because no light would be passing through. Then I have, let's say this is an infinitely narrow slit, then I suddenly have some amplitude, right? The usual sort of a e to the ik delta over 2 is what we've been writing it as. Nothing, 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 nothing. Let's put that one as a minus. Then I've got a e to the ik delta over 2, nothing, 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 right? So you treat the whole thing with and assign a complex amplitude to every point on it. And then your problem, and this is true as well if you have just an open slit, you need to assign every single point in your aperture with a complex amplitude, and then you need to sum them up, right? And that's how you get your total amplitude. And of course, for a generic object, which is not just simple two slits or whatever, could be an open slit, which is where we're going next. You've got to sum up an infinite number of infinitely small sources, and so your discrete sums are going to become integrals, right? That's where we're going. So, right. Yeah, that's what that bottom slit says. So for continuous objects, we're going to now need to perform integrals. So where we're heading with all this is to look at the single slit problem, where we do have a single slit of finite width, and we're going to look at how to deal with that. We might not get into the calculation this lecture, we'll see, because I need to say a few things first. Okay. Right, now, this is all heading towards something called Fraunhofer diffraction. Now, there's a general theory of diffraction, which is the Fresnel theory. That basically doesn't make any approximations. It really does the whole thing from first principle. It looks at how light behaves as it passes through an aperture, bends around an object. It makes no small angle approximations. It does everything from scratch. It is horrific. You would need to throw a computer at it, right? So more practically, we look at the simpler case of Fraunhofer diffraction. In simple terms, Fraunhofer diffraction is when you can make the small angle approximation. The easiest way to get into the Fraunhofer regime of applicability is to be at large distances, so then your angles tend to be small. The specific mathematical definition, if you were asked what is the definition of Fraunhofer diffraction, this is what it is. It applies when the phase of the light amplitude varies linearly across your diffracting object, this being your diffracting object. I will hopefully clarify, hopefully I have time in this lecture to clarify that, we'll see, what that means, if not, the very start of next. And what you see is if you get into the Fraunhofer regime and you start adding your complex amplitudes, you will end up with a set of integrals which are simply Fourier transforms. Now, some of you will have heard of this already, or heard the phrase at least, Fourier transforms. Some of you may not have, don't worry. It's something you do in detail next year. This is in red because it is next year. But once you do get to knowing what Fourier transforms are, you will find that essentially everything I've talked about in this entire lecture course can be condensed into about 3 lines of a Fourier transform, and you'll think, why did we bother, right? But anyway, you haven't done them yet. In principle, you haven't done them yet. So we do it this more lengthy brute force way. Okay. So when does Fraunhofer diffraction apply? Yes, I think I've got time to just do the proof that I wanted to do to sort of convince you. Right, when does it apply? So basically, it applies, the easiest way to get into the Fraunhofer regime, as I said, is when you've got long, large distances. So here's my light source. Producing spherical waves, and as long as I'm far away, then it's a plane wave by the time it gets to the diffracting aperture. Why is that important? Well, it means that the phase of light, if I've got plane waves, the phase of light as it reaches the aperture is all the same, right? And that's kind of what I want. And then I get spherical waves coming out again from my aperture, but again, then as long as I'm far away, when I view it, then I've got plane waves again. Right. Now, that's an important point, but it's not actually the fundamental definition of Fraunhofer diffraction. What we need, it transpires that the condition you actually need is that you need distances, so distances greater than a squared over lambda, where a is roughly the size of your diffracting aperture. Right. Now, that looks like it's been plucked from nowhere, so despite what I'm about to do now is not on syllabus either, I just want to show it to you anyway, because it's a good place to end. So why have I plucked that number seemingly out of the air? So let's consider a diffracting aperture, right, of width a, roughly. I want to know what my amplitude is at some point P. I'm just going to draw on a construction line coming first of all from the middle of my slit. I'm going to call that distance R. I'm then going to take another point, some arbitrary point somewhere else in the slit, X, a distance X away from my sort of origin, which I've defined to be the middle. Okay. Now I also know that that angle is theta. I am not making the small angle approximation yet. I'm going to do the whole thing. So what we're saying is that little r squared is big R squared plus x squared minus 2rx cos pi by 2 minus theta. So r squared plus x squared minus 2rx sine theta. So let's say that little r over big R equals 1 plus x squared over r squared minus 2x over r sine theta all to the half. And I'm just going to expand this. So that is approximately equal to 1 plus a half x squared over r squared minus 2x over r sine theta. I need to go up to one more term. So minus an eighth. I want to go up to the x squared terms, basically, to try and illustrate to you, firstly, what's meant by the Fraunhofer diffraction ratio. Sorry, I've lost my track. I will write this down and then talk. Right. I want to go up to the squared term to show you what I mean by the Fraunhofer definition, that we need our phase of light to vary linearly with distance across the object. Right, so I'm going up to here. I'm going to gather up just the squared terms. So I've got one lot of x over r sine theta and plus a half x squared over r squared minus x squared over r squared sine squared theta plus dot 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 for the other terms. That is 1 minus x over r sine theta plus half x squared over r squared cos squared theta plus dot dot dot. Right. So what that means is that I have little r equals big R minus x sine theta plus half x squared over 1 lot of r cos squared theta. Now, what my path difference is between these two things that I drew up there is, little r is a bit shorter, isn't it? So it's r minus little r, which equals x sine theta minus a half x squared over r cos squared theta. We have gone up just to the x squared term, so there are other terms as well. Right, now here we come to what I mean by the phase difference, because I could multiply this just by k to get the phase difference everywhere. Right, in the Fraunhofer regime, I said it means that the phase difference is a linear function of the distance across the aperture. That means I want just that term to be a sufficient approximation. Right, so linear term, linear in x. That is, I want that term and any further terms in x cubed, etc., not to matter. So I need to get myself into a regime where that's true. So what I need is that even at x equals plus or minus a over 2, i.e. the largest it can be, I can ignore that term. So what I'm saying is that I want half a squared over 4r cos squared theta to be much, much less than lambda. I want it to not contribute much to my path difference. And okay, here we just do a little bit of hand wavy and don't worry about the constants too much. And I say, okay, roughly a squared over r is much, much less than lambda, because it's a bit of a hand wavy thing anyway as to what you define to be small. And so, therefore, r must be much, much greater than a squared over lambda. So that is where that condition comes from. It is not on syllabus for you to prove that, but it just looks like it's come from nowhere unless you sort of see that. Right. So our point is, at least on the way, I have hopefully clarified what I mean when we say the Fraunhofer regime means we can write the phase difference linearly as a linear function of distance across the object. This is what it translates to. It turns out that a over lambda can be quite a large number in many cases, so you tend to have to go to large distances to get there. Okay, hang on, let me just see, because it would be nice to do this one final slide, because then we can just start properly with single slit diffraction. So this is just a few things I've almost already said. So I've said plane waves get you into the Fraunhofer regime. Turns out they're a sufficient but not absolutely necessary condition. We can get into the Fraunhofer regime in different ways, and we will touch upon that later, by basically every time you have a practical piece of optical equipment with finite-sized elements, so a telescope, like with a finite-sized lens, for example, turns out that your image is limited by Fraunhofer diffraction. So we will talk about that later. I think that's all I wanted to say on that slide. So, done for today, and see you next week.